let's define a field. A field is a set F along with two commutative binary operations like addition, multiplication, such that F with binary operation addition is abelian group. Also, if you subtract 0 from field F, along with multiplication is another abelian group. You also have distributive property A dot B plus C is A dot B plus A dot C. So eventually, if you want to change these operations to other operations, you're able to do that. There is no doubt there. You saw fields before, you used them many times. Basically, a field like F is the smallest mathematical structure such that you can perform all arithmetic operations that you can perform all mathematical operations like addition, subtraction, multiplication, division. And please note that when we're talking about division, we're talking about non-zero elements. Some examples that you saw before are rational numbers, rationals as a field, and also reals as field. For those of you who saw Z sub P, this is also a finite field. This is basically discussed in discrete math and abstract algebra. A little bit of background: if P is a prime number, then we can define equivalence relation on Z, and we're going to connect P finally, and we're going to see what's going on. So an equivalence relation tilde, for example, on Z is defined as N is equivalent to M if P divides N minus M. All right. So in that case, we can define the equivalence class of N and then we can define Z P, which is the set of all equivalence classes such that N belongs to Z. So basically, the operations that we're defining here are addition as a binary operation takes elements from the Cartesian product between ZP and CP and it maps it to Z sub P, and N plus M is just the equivalence class of N plus M. And for multiplication, that maps ZP, the Cartesian product, to ZP is defined as the equivalence class of N times the equivalence class of M is basically the equivalence class of N times M. This guy is basically a finite field.